Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are undertaking a deep dive into the very first, the absolute foundation of Unit 7, alternating current. We'll be looking at AC voltage applied to a resistor. This concept is, your 0-degree baseline for the entire chapter. We promise to make this so simple and so exam-safe that you will lose all fear of AC circuits. Okay, let us begin with a simple question, something you see every day. Think about an electric heater or a geyser at home. At its core, it's basically just a high-resistance wire, right?
Yes, just a coil that gets hot.
Exactly. Now, when you plug it into the wall socket, that AC voltage is constantly reversing direction. It goes positive, then negative, then positive again.
Okay.
50 times every single second.
That's the 50 hertz frequency. The current is always changing direction.
Correct. But here's the surprising part. The heater, well, it never stops heating. The heat generation doesn't reverse. It doesn't even pause during the negative half cycle. It just generates heat continuously.
Wait, what? If the current direction is changing, shouldn't the heating also pause or change somehow? I would have thought it would fluctuate heavily.
That's the puzzle, isn't it?
Yeah.
How can a reversing current produce continuous non-reversing heat? That question is the perfect entry point. So let us unpack this. The core idea is that a pure resistor is the simplest AC component. And it's simple for one reason. It responds immediately and proportionally to the voltage. There is absolutely no delay.
No delay at all.
None. Whenever voltage increases, current increases right there with it. When voltage decreases, current follows. They're perfectly synchronized.
But why? What's special about a resistor that makes it react so instantly?
That's the key why. It's because of what a resistor is. Its property, resistance R, is constant. And more importantly, a resistor has no capacity to store energy.
No storage.
Exactly. It can't store energy in a magnetic field like an inductor, which gives it sort of inertia. And it can't store it in an electric field like a capacitor, which gives it a kind of memory. It only knows how to do one thing, convert electrical energy to heat instantly.
Oh, so because it can only dissipate energy, it has to obey Ohm's law at every single instant. It has no choice.
You've got it. Now, for an analogy, imagine a section of a highway. The cars are the electrons, the current, and the traffic signal is the voltage command. When the signal says go, all the cars speed up instantly, all together. When it says slow down, they all slow down instantly. There is no car hoarding momentum or inertia.
So the voltage and current are, what's the term, in phase?
Exactly. They're in phase. And the mental image you should have for your exam is just two identical sine waves. One for voltage, one for current, laid perfectly on top of each other. They rise to their maximum, cross zero, and hit their minimum at precisely the same time. Always synchronized.
Okay, that visual helps a lot. Two waves moving together.
Good. Now that we have the core picture, let's see how insert formally defines this. Can you please read the expression for the instantaneous AC voltage and the current that results from it?
Yes. It says, the instantaneous voltage across the source is given by $V sin omega t. Applying Kirchhoff's loop rule to the resistor circuit, the resulting instantaneous current is 1 aval n as 1 omega tt, where the current amplitude or m is given by 1 frakvit.
Excellent. Now this is where it gets really interesting. Let's break down the mathematical implications step by step. 1, the voltage varies sinusoidally. Vm sin omega t. 2, because R is constant, Ohm's law works at every tick of the clock. So current IM has to be Vm AD.
Right.
So step 3, this means the current IT also becomes sinusoidal. IM says AD TP. Now look at both of those equations. What do you notice about the sine part?
They both just have sin omega t. There's no extra term, no phase angle, nothing.
Precisely. That is the mathematical proof that they're in phase.
Yeah.
That phase difference, phi, is 0. This simplicity is why the resistor is our reference for the entire chapter.
So things like Vm Gras and Vm Barrows are just Ohm's law, but for peak values and RMS values.
Spot on. That's exactly what they are. And this is why we use RMS values. Remember, the average current over one full cycle is 0, but the power, the heat, is definitely not 0.
Right, because the heater works.
So we use the RMS current, which is RMS squared to DO, to calculate the average power. The formula is simply PAVG to RM buildup. That gives us the effective heating capacity. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PRO-SAM.com. Let's do a quick numerical example to make this concrete. Suppose you have a heating element, let's say 4 to 4 or 6 mAh, and you connect it to our standard Indian household supply. That's 230 volts RMS.
Okay.
What's the RMS current?
That would be a 1 arm arm 6, so 230 divided by 46. That's exactly 5 amperes.
Perfect. And the average power it dissipates.
Average power would be RMZ true. So 522 times 46. That's 25 times 46, which is 1,150 watts.
Hey.
A 1.15 kilowatt heater.
Very good. Now, here's the fun fact that often trips people up. The effective voltage is 230 V. But what is the actual peak voltage that your appliance is handling?
The peak voltage, V volters, is a long time conversion.
Yeah, and squared is about 1.413.
Yep.
So it's 230 times 1.412.
That's around 325 volts.
Exactly. Your 230 volt supply is actually peaking at 325 volts 50 times a second. The RMS value tells you the heating effect, but the peak value is what the components physically have to withstand. And this whole resistor topic, it sets the foundation. It's our 0-degree reference. When we move to inductors and capacitors, we'll see their voltage and current are not in phase. The resistor is the reference point. Okay, now for the silent killers. The misconceptions that can lose you marks in the exam.
Okay, I'm ready.
Misconception number 1. Thinking that the resistance itself changes or reverses with the voltage. That is completely wrong.
But the voltage and current are changing.
They are, but resistance R is a rock-solid, constant material property. It doesn't care about the AC nature of the supply. Ohm's law works at every single instant. R does not change.
So resistance is constant, even though voltage and current are in flux.
Got it. Second killer. This goes back to our first question. Some students think since the current reverses, the resistor must supply energy back during the negative half cycle.
Yeah.
Again, completely wrong.
Oh, I can see why someone might think that. A negative current.
But a resistor is an energy sink. It only dissipates. The formula is pi I2I more Bali night. Squaring the current, the tau I2R part, makes it always positive.
Right. Even when I is negative, I squared is positive.
So power dissipation is always positive. The resistor only gives off heat. It never stores or returns energy.
Okay, that's crystal clear now. The resistor only dissipates. It never gives energy back.
To lock this concept in, let's use a few memory anchors. First, it's a simple phrase. Resistor. In phase, always dissipating.
In phase, always dissipating. Okay, that covers both points.
For the phase relationship, you can use a physical gesture. Imagine your right hand is voltage and your left is current. Now move them together. Raise both hands up, then lower them down, perfectly synchronized. That motion is in phase.
Okay, I can picture that. Synchronized hands.
And one last thought. Think of the resistor as a heat-generating slave to the voltage. It has no inertia, no memory. It just obeys the voltage command instantly and burns energy as a result. All right, let's quickly summarize the 3 core facts about AC applied to a pure resistor. The things you must remember for your exam. Number 1, the instantaneous voltage, V, and current I are in phase. That means 0 phase difference. They peak and cross 0 at the same time.
In phase, got it.
Number 2, Ohm's law applies to the RMS values. It's your go-to for calculations. Math BFI arms are rearm.
RMS values obey Ohm's law. Check.
And number 3, a pure resistor is purely dissipative. Power is always positive, and you calculate the average power using PIGH2RIs.
Always dissipative. Okay, those 3 points are clear.
To get maximum marks in 12th CBSE, physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. We hope this deep dive into the resistor was helpful. It's the simplest piece, but getting it right makes the whole AC chapter so much easier. All the best for your exams.